In the previous video, we've defined all the notations that we are going to use to construct the optimal simplex table. In this part, we are going to construct the constraint part of the table. Now in this video, we are going to construct the constraint part, both the left-hand side and the right-hand side, using all the notations that we've talked about in the previous video. So this is the general form of a linear programming model. And then if we know which variables are basic variables, which variables are non-basic variables, we may rewrite the model to become this. So we don't do anything other than rewriting this, grouping the x's that are basic variables together, and then group the other variables that are non-basic together. So we just rewrite them, rearrange them. So for example, x1, x3, and s1, they are basic variables, so we just group them together. And then anything that are non-basic, we just throw them to the other part, to the other term, okay? So we don't do anything other than just regrouping. Both in row 0 and the constraint, we just regroup basic variables to one side and non-basic variable to the other side. So in the Dakota problem, that is our original problem. And then if we know that in the optimal table, these are the basic variables and these are the non-basic variables, we may just regroup them. Okay, so this is the group of basic variables, this is the group of non-basic variables. If you multiply them, it will just return to this form, really. So 0 times s1, 20 times x3 plus 60 times x1 plus 30 times x2 plus 0 times s2 plus 0 times s3. So it's really just rewriting this row, okay? So you need to convince yourself that this is just rewriting this in the other form. So similarly for the constraint, we just group the variables and the columns. So this is the column for s1, this is the column for x3, this is the column for x1, times the basic variables. We do the same thing for the non-basic variables, equals this. If you do the matrix multiplication, you need to convince yourself that this will give you these three constraints that we have in the original problem. Okay, so we have shown that we may rewrite the problem by regrouping the variables based on whether they are basic variables or whether they are non-basic variables. Once we have convinced ourselves that we may rearrange a linear programming problem into the variables that are basic variables plus the variables that are non-basic variables, the next thing we are going to do here is multiply the entire constraint, the entire row, with B inverse. So both the left-hand side and the right-hand side, we multiply it with B inverse. So here's how it looks like. B inverse times BXBV plus B inverse times NXNBV equals B inverse times B. So B inverse times B, they cancel each other. So this is the final result. XBV plus B inverse NXNBV equals B inverse B. This result may not look anything special to us at this moment, but then if you look at our optimal table for the Dakota problem, you see that for the basic variables, they do not have anything multiplied to them. So they are just XBV. So they're just S1, X3, and X1. So in other words, when we multiply the entire row with B inverse, we try to isolate the variables that are basic variables. So we isolate XBV by itself such that it represents the canonical form that we have on the optimal table of the simplex algorithm. If you're still not very convinced what is this about, let's take a look at a concrete example of our Dakota problem. So from the Dakota problem, we have B looks like this. and then you need to take the inverse of the matrix and obtain B inverse. Now let's see, this row here looks like this. So this is our XBV, S1, X3, X1. This is our B inverse. This is our N. This is our X and BV. This is B inverse again. And finally, this is small b. If we do the matrix multiplication, this is the result. Okay. Now let's compare this result here with the optimal simplex table on the next slide. Okay, so here's the result from our previous slide. And then let's compare this with our optimal table. So I cover the row 0 part because we're just talking about the constraints. You can see that this is exactly the same. So the first row says 1 times S1 minus 2 times X2 plus 2 times S2 minus 8 times S3 equals 24. Okay, so that's how you're going to read this first row. And then let's say the third row says 1 times X1 plus 1.25 times X2 minus 0.5 times S2 plus 1.5 times S3 equals 2 on the right hand side. Okay, so if you perform the matrix multiplication, you will exactly get constraint 1, constraint 2, and constraint 3. So in other words, from here you can see that now you may get the value of the right hand side, 24, 8, and 2, using this formula, B inverse times B. And then for any of the basic variables, actually you do not need to compute anything, right? Because you know for basic variables, they are always in canonical form. So if the order is S1, X3, X1, it means S1 has 1 in the first row, first constraint row, and then X3 has 1 in the second row, and then X1 in the third row. Again, how do I know that? Because basic variables, they are always in canonical form in the optimal table. Okay. Now for the non-basic variables, you may compute B inverse times N, but if you want to compute for just one particular column of non-basic variables, for example, you want to compute the column of S2, you may compute it as B inverse times AJ, where AJ or A of S2 is the coefficient of S2 in the original problem. Okay, so if you do B inverse times N, you will get all the coefficients for all non-basic variables, all the columns. But if you multiply B inverse times AJ, you will get just one specific column of a non-basic variable that you're interested at. Okay, because if you look at the multiplication, this is B inverse, this is N. If you're just looking at one particular variable S2, it means you're just looking at that column. So the result will be that 2 to minus 0.5. Okay, so let's conclude that we may use the notations and formula to construct the optimal rows of the constraint using the formula of B inverse times AJ for every column. And then for the basic variables, actually you do not need to compute anything because they have to be in a canonical form. So just look at the order, and then it is always 1, 0, 0, or 0, 1, 0, or 0, 0, 1. Okay. But if you compute using B inverse AJ, of course you will get the same result. Okay. So if you're not convinced, just try that. And then for the right-hand side part in the constraint rows, you may use the formula of B inverse times small b. Okay, and then if you forget how to get all these values for these notations, you need to rewatch the previous video. So in the next video, we're going to talk about how we may also construct the row 0 part. So see you on the next one, and thank you.